With high energy X-ray beams, let's see, what do I want to say about this? Okay, we'll talk about energy of X-ray beams. So we have, if we're only treating surface tumors, I mentioned before that you might use beams that are going to be in the 50 to 150 keV range, and that's basically going to penetrate very, very little. Just going to be probably the upper maybe a couple, maybe a millimeter or less of skin. Then we can go to higher energy machines, and these were machines that were used a lot in the mid part of the 20th century. I remember, actually remember these machines around. They probably started to phase out in the 1960s. There's still some of these around that are being used, and they operate at around 400 keV, and that's going to be more penetrating. So at 400 keV, we're going to be able to go a little bit further into the tissues, and finally we're going to get so this is the low energy, and then we're going to go to the high energy, which are the megavolt machines. So these are the ones that are going to be producing greater than 1 million electron volts, and these are the machines that are obviously going to be most penetrating. So the megavolt machines really replace the other machines for several reasons, and a few of these are given in the book. One of them is the fact that with lower energy photons, as I said before, they interact with matter before they actually reach the target organ. So basically, if I've got a body here and I'm trying to hit a tumor that's down here, and I've got these lower energy, this lower energy beam that's coming in here, it's likely to interact with other tissues before it actually penetrates to the depth of the target tissue. So it's might react. It might stop over here. It's not going to penetrate that much. The percent depth dose, which is the percentage of the maximum dose that actually reaches the target organ, is going to be much lower in the case of say an orthovoltage machine compared to a megavoltage machine. The other thing has to do with a phenomenon known as penumbra, and basically what that is, it's kind of like a shadow that forms with X-rays. You also get it with visible light. You can actually see this from the sun. The sun's shadow is sometimes referred to as the umbra, and then there's an area around that. It's kind of like a lesser shadowing that's referred to as the penumbra. So if we have a source, and then we have, for instance, we're actually going to have beams that are going to come down, where they're going to come down from a number of different places. We can have something like that that's actually hitting, let's say this is the surface of the skin. So this is the skin right here. And here's our source, here's our X-ray source, and we've got beams that are coming down like that. We're also going to get beams, beams are going to occur at a number of different angles, but we can also get beams. This is, basically, we're expecting these things to go approximately at right angles to the source, but we're also going to get some beams that are going to come down, for instance, like this, and we might get a beam that's going to come down and cross over like that. And so this targeted area would be the umbra, and the penumbra is actually in here. The penumbra and penumbra. So in order to treat a tumor, you want to try to get as collimated or narrow a beam as possible. What's happening here is this is causing the beam to spread out. So we've got this kind of shadow effect. You really want a beam that is kind of uniform, where you're getting the same amount, if this is the beam here, you're getting the same amount of energy hitting, that's going to be coming out of here everywhere along the beam. Here we're not seeing that. We're seeing that we're going to get more energy in the middle, and then where we go to the outside where the penumbra is, we're going to be getting less energy at that point. So that's the second reason why we'd actually like to use a higher energy beam, because the higher energy beam actually produces less penumbra, and so it's actually it's much larger for lower energy beams. So this is another way that we can adjust for penumbra, and also we can decrease the source to collimator distance. The collimator being that structure that's actually going to kind of narrow the beam a little bit. If we make the distance from the source to the collimator larger, I'm sorry, not smaller, but larger, that's actually going to decrease the penumbra. So that's, and if we decrease the source to surface distance, that would also decrease the penumbra. So that's a couple things that we can also do to lessen this effect. And the third point made has to do with the fact that if we're using lower energy beams, we can't use isocentric focusing. So we can't use any of the isocentric techniques that we learned about in the previous chapter, where we saw that we can get much better application and less tissue damage if we actually apply X-rays. If we're trying to hit a tumor right here, we're going to apply X-rays at different angles that are all going to converge somehow concentrically on that tumor. You can't really do that with a lower energy beam because you can't penetrate far enough in to actually be able to apply an isocentric technique. And if you look at the figure on page 220, figure 3.8, you can see the effect of using the isocentric techniques where everything, these things are not just straight lines like this. It's kind of showing you, what it's trying to show you in this diagram is what I was showing you before, that you're getting these areas of X-ray production where there's convergence, where a divergence rather of the beam. It's coming out and it's getting wider. Then you've got a beam here, and then you've got another beam over here. So that's doing the same kind of thing. And then you've got one over here and one over here, and those are producing beams that go like this and like that. And the point of intersection, this area right in here, is kind of an octagonal area where the concentration of these X-rays is going to be greatest. So that's the advantage of using that isocentric technique. The maximum dose that's deposited at a point where the number of electrons knocked loose, that is the Compton electrons, equals the number of electrons that are actually being stopped. And this is called the electron equilibrium. So at greater electron equilibrium, we're going to have more Compton electrons are going to be produced than the electrons that are actually being stopped by matter. So this is something else to keep in mind. And I already mentioned that the higher energy beams are more penetrating. They transfer more energy, and I talked about electron equilibrium. The next thing that I really wanted to mention is that in the megavoltage range, no, I already said that. Let's see, what other things do we have in here? The techniques that are actually used to produce X-rays. One of them involves something called a magnetron. And this is similar to it's actually the same kind of thing that's actually used in a microwave oven. So a magnetron is a device that's actually used. These things are used in microwave ovens, and they can be used to. And you also get something similar. They're also the kind of things that you see in these 4 to 10 megavolt accelerators. If you want to go to a higher voltage, you need something called a klystron. So the magnetron is actually what it's doing is it's using a magnetic field to focus microwaves. So we have microwave radiation that's being focused on that. And this isn't really the best analogy, but the idea is that by doing that, the electron, it's almost as if the electron is surfing. The electrons are actually surfing along this, and as this moves, the electrons accelerate in that direction. The klystron is a little bit different. The klystron, it's actually, these are used in higher voltage machines, and the klystron actually, it's a linear beam vacuum tube. This is an evacuated electron tube, and these things are also microwave amplifiers, but they can be used as microwave amplifiers, but they're also used as radio frequency amplifiers. So we're actually by using them as by using the radio frequency, using these things as radio frequency amplifiers, we can actually get beams that are we're going to actually be able to accelerate them to greater speeds and therefore higher energies. So if you look at the table, let's see, table 13.1 on page 221, you'll actually see the maximum dose depth in water for various photon energies. Most tissues in the body are going to be about, even though this is given for water, this is probably a fairly good approximation for soft tissues in the body. So if we wanted to penetrate, if we use ortho voltage, we essentially get no penetration at all. And then using gamma radiation from cesium-137, the 0.7 MeV gamma, that penetrates about 1/10 of a centimeter. That's 1 millimeter. Cobalt-60 will give us about 1/2 of a centimeter. A 4 megavolt X-ray penetrates to about 1 centimeter. We're going to get about 10 centimeters, 2.5 centimeters from 10 megavolts, and 5 centimeters, which is about 2 inches of penetration at 25 megavolts. The nice thing about using the klystron is the klystron output can be precisely controlled for frequency, amplitude, and phase, which is something that you also can't do with the magnetron. So these things are much more focusable, and we actually see, I think a couple pages later, we'll actually see an example of both of these. Okay, so microwaves are moved by what are known as waveguides. So we actually can put these things into a tube, and we can get them to resonate within the tube. It's kind of like the analogy that's given in your book is if you have a, let's say we had a vertical tube here, and you blew air across that, you can actually get a, once you hit the fundamental frequency of the tube, the vibrations in here, these compressions and rarefactions that occur in the air in the tube are actually going to cause resonance in the tube, and the tube will ring with a particular sound. It's actually amplified. And we get a similar kind of amplification and actually a kind of a narrowing of this band that wants to move out if we use this waveguide here. So it says they can be as simple as copper tubes, and they can also be more complex than that. The intensity of the waves is seen at the end as is put in at the beginning. So we're not really going to change the intensity of the wave, the amplitude of the wave, but we're preventing the wave from fanning out, which it would have a tendency to do. Remember, let's see, what other things do I want to say here? So we can have two kinds of waveguides. One of them is referred to as a traveling wave accelerator guide. Both of these things actually do accelerate the wave to make the wave go faster, but they're not going to, as I said, they're not going to change the amplitude. And we've also got what is known as a standing wave accelerator guide. And the idea with a traveling wave guide is a traveling wave is a wave that's going to have a particular shape, and the whole wave is going to appear to be moving down the tube. We can also set up what's known as a standing wave, where the wave appears to be stationary in the tube. And you can see this, you can make standing waves by taking a rope and attaching it to one end of a wall, or having somebody hold it stationary and then moving the rope up and down. If you get the frequency of moving the rope up and down just right, you can actually generate a standing wave, a wave that looks like that. So you've got one standing wave going in this direction, and then you've got another standing wave that you set up in the opposite direction. And you'll get along here what are known as interference patterns. So for instance, if you have a wave like that and another wave that's got the reverse phase, these two waves would cancel out. If we had a wave that looked like this and another wave that was exactly under that, those two waves would add to a higher amplitude wave. These two waves, we call this destructive interference, and this we call constructive interference. So actually, by adjusting in the standing wave, if we adjust the frequencies to the just in a certain way, electrons are going to be actually accelerated as they move through the tube. So it's another form of electron acceleration. For conventional X-ray machines, we can only accelerate electrons up to about half of the speed of light. So if we want to go faster than that, it's going to require a lot more energy than we see in most conventional X-ray machines. So we're going to get velocities up to about 0.5 C, C being 3.00 times 10 to the 8th meters per second. So this would be about 1.5 times 10 to the 8th meters per second. The amount of energy that you get out of that is quite small. It's only 79 keVs, which is 0.079 million electron volts. So that's a fairly small energy. And if you actually increase the energy up to 35, so this would be the sort of thing that we would see for these very for these relatively low energy electron beams that we might see from a conventional device. But if we actually took one of the megavolt machines and at about 35.63 MeV, we can actually accelerate this up to 99.99 C. I'm sorry, that's not, it's 0.9999 C. So that we not, well, I meant to say 99.99% of the speed of light. So 0.999 C is the velocity that we can reach, but that's going to require a much greater energy to do that. Okay, so let's see. If we go now to page 224, we'll actually see a diagram that's going to show us. The two types of machines that I mentioned before, the one that uses a magnetron and the one that uses an accelerator, the one that uses the klystron as the source of electromagnetic radiation. So the magnetron machine, you'll notice that both of these machines are actually irradiating, so that you've got the thing that's actually producing the X-rays is up here. The patient's lying on a table, and the X-rays are coming down like that. The difference is in the way that they're produced. So for instance, using a magnetron machine, we have a horizontal waveguide. So here's our waveguide. And then we actually have the magnetron. It's producing the waves over here. Here's the magnetron. And then all the other parts of the X-ray machine are over in here. When you look, you can see you've got an accelerator guide. Below that is the target. Below that is a device that's called a monitor. Probably ought to draw this with a little bit more detail here then. So we'd actually have something that looks sort of like this. Here's our accelerator guide. Right below that, we have the target. Then underneath the target, we have a monitor. The monitor is actually detecting how much radiation that we've got in here. And below that is the collimator, which looks sort of like this. And then the X-rays are coming out, collimated X-rays are coming out and hitting the patient. So that's kind of what we do with the magnetron device. And then the klystron, that type of device is a little bit different looking. So you can see again in figure 13, 14, what we've got there is the klystron is now put in. So here we actually had, but the magnetron here is actually set in the in this part of the machine, and not in the vertical part, but in the horizontal part. In the case of the other type of X-ray machine, we actually put the klystron down here, and then coming out of the klystron is the waveguide, which in this case is actually turned at right angles, and then we've got the electron gun. This is an accelerator. So we then attached to that we have what's called a bending magnet, and I'll get to that in a second. A bending magnet, because we actually we have the waves going this way. We want them to bend at right angles, so we use this bending magnet. And then again, this is going to pass through, just as it did before. It'll pass through a target, a flattener, a monitor, and then finally collimators. And again, the beam is going to come down like this.